Hello, everyone, and welcome to this episode. Today, we are answering some multiple choice questions related to intermolecular forces. This is AP Chemistry, section 3.1, and the concepts from 3.1 carry through the rest of Unit 3 for AP Chemistry. And this can be a tricky topic for a lot of students because it's a little bit different than getting an equation and solving for an answer and just putting a unit on it and moving on. You'll be asked questions about properties of substances like boiling point, melting point, vapor pressure, viscosity, surface tension, enthalpy of vaporization, enthalpy of fusion, and some cohesive forces occasionally. And those properties are dependent on their intermolecular forces. And so, to understand and answer these questions, you have to be able to imagine the molecules of the substance that you're dealing with. Sometimes you'll get a Lewis structure, sometimes you'll have to draw your own. But you have to imagine the molecules, the shapes of those molecules, what intermolecular force they will exhibit, whether it's London dispersion, dipole-dipole, or hydrogen bonding. And then, and only then, can you say, oh, it's got this force, it will affect the property in some way. So there's a lot of visual concepts here that are not mathematical in nature. So some of my students have difficulty, working through all the visualness of it. And so I decided to focus on those for this episode. I'm going to summarize some of the properties here. Then we'll get into the multiple choice. I do have a few pause the video moments for yourself to try some of these. I tried to group them into similar pairs. But here we go. I made this table for my classes as a way to try to summarize everything. For example, if you're comparing boiling points of something, the one with the stronger intermolecular force will have the higher boiling point in general because the stronger intermolecular force holds the molecules together and makes them attract each other more. So you need a higher temperature for which they can break apart. Weaker intermolecular force, again, a lower boiling point. Same with melting point. You have to break the molecules apart from each other to melt them. So higher intermolecular force gives you a higher melting point. And the opposite is true. And as you look down this list, viscosity is higher with stronger intermolecular force. The molecules hold together tighter and resist flow. The surface tension is higher with stronger intermolecular forces because the molecules want to stick together and minimize their surface area. And higher enthalpy of vaporization. Stronger intermolecular force needs a lot more energy to break the molecules apart. And same with enthalpy of fusion. And cohesive forces are also higher with stronger intermolecular force. The only one that's different, if you're noticing, is vapor pressure. That's the one that gets everybody because it's the only one in which the stronger intermolecular force will give you a lower vapor pressure. All right. And that's weird because, for something to turn from a liquid to a vapor, it has to escape the molecules that it's with. And if it has a stronger intermolecular force with those molecules, fewer of those molecules will escape into the vapor phase. And so you get a lower vapor pressure with stronger intermolecular force and vice versa. So maybe make a note of that one, and then everything else is the opposite of that one. My students latch onto that pretty quickly. So let's get into some questions. These are AP style multiple choice questions. We'll start with number one here. It says the London dispersion forces are weakest for which of the following gases under the same conditions of temperature and pressure. And by the way, if you need a refresher on the types of intermolecular forces, you can check out my previous videos. I'll try to put a link in the description. Which LDFs are the weakest? Okay, and we have hydrogen, oxygen, xenon, and fluorine. The thing to remember is that London dispersion forces are weakest for those with the nonpolar ones with the fewest number of electrons. The more electrons you have, the more the London dispersion force is stronger because the electron cloud can become more polarizable and lopsided. And so I'm looking at down here, so I'm thinking about atomic masses. Hydrogen is the lightest element, and it's only got 2 electrons per molecule. The rest of these have 16, 18, and xenon has a whole bunch. And so I'm going to go with hydrogen on this one. All right. And let's do our first pause the video moment. Here's a similar question. Which element, neon or xenon, has the lower boiling point and why? Take a moment, read the 4 choices, make your choice, and see. I'll be back here in a second. Okay, and right here, the correct answer is A, because neon is smaller, less polarizable. It actually will boil at a lower temperature than xenon, which will hold together to a higher temperature because it's got a lot more electrons. So we're going to go again with A on that one. All right, let's get to another similar one. Here we have a couple of Lewis structures that are drawn. Compound 1, compound 2, and it says the structural formulas of 2 compounds that are liquids at room temperature are shown above. Which of the following statements best explains the observation that compound 1 boils at 35, whereas its structural isomer compound 2 boils at 118? So we have a big difference in boiling points there. And you might look at them and say, well, they're made of the same atoms, right? And we're trying to explain why this one has a higher boiling point. Now, go back to the molecule shapes. This one's generally nonpolar, maybe a tiny bit polar because of the bent oxygen in the middle, but maybe a weak dipole-dipole force. Over here, most of the molecule looks nonpolar, but here's the culprit right there, the OH on the end. Whenever you see an OH on a molecule like this, then you know that it exhibits hydrogen bonding with some of its neighbors. And hydrogen bonding is a stronger force than this one. And that means letter D is our correct choice. Although there are dipole-dipole attractions among the molecules of both compound 1 and compound 2, the OH group in compound 2 allows strong hydrogen bonding to occur. And that would be your choice there. And let's do our second pause the video moment with a similar question. We have some hydrogen halides. Their normal boiling points are here. The liquefied hydrogen halides have the normal boiling points given above. The relatively high boiling point of HF can be correctly explained by which of the following? Take a moment, pick your answer, and we'll be back here in a couple of seconds. And again, if you chose D, because HF molecules tend to form hydrogen bonds. Remember, hydrogen bonds happen when a hydrogen is attached to a fluorine, directly to an oxygen, or directly to a nitrogen. And HF is the only one of these. Yes, they all have hydrogen, but only this one has a fluorine, oxygen, or nitrogen. So good job on that. Let's move on to another question. This one, again, is about boiling points. Considering the molecules represented above and the data in the table below, nonane and 2,3,4-trifluoropentane have almost identical molar masses, but nonane has a significantly higher boiling point. Which of the following statements best helps to explain this observation? Okay, so you'll see this a lot. They'll say molar masses are the same, different property. Why? We have choices. The CF is easier to break than the CH bond. And I'm not going to go with that one because we're not breaking bonds here. We're just moving molecules apart from each other. The CF is more polar than the CH bond. The carbon chains are longer in nonane than they are in 2,3,4-trifluoropentane. And the carbon chains are farther apart in a sample of nonane than there are. So we're supposed to justify the fact that nonane has a higher boiling point. And yes, this is pretty nonpolar. And this is also going to be fairly nonpolar too, because this molecule can rotate and the fluorines can be on either side in any of these positions. The difference here is molecular complexity. This is a factor in intermolecular forces. This one has a longer chain, and the longer chains have more ability to interact with each other over more surface area, and they also get tangled up a little bit easier in themselves. And so I'm going to choose letter C on that one. Okay. Let's take another pause the video moment about boiling points and see if you can grab this one. So we have butanol, pentane, propanoic acid. Their molar masses, again, are very similar. Please note that. And it says, based on the information in the table above, which of the compounds has the highest boiling point and why? Take a moment, pause the video. Back here in a couple of seconds. And if you chose D, congratulations. I would expect this one to be the highest because, yep, there's a hydrogen bonded to an oxygen directly. This hydrogen is not bonded to the oxygen directly, so that's not going to be a hydrogen bond, and this is just a nonpolar pentane. And so we're going to go with propanoic acid because it can form intermolecular hydrogen bonding. So good job on that. All right, let's talk about vapor pressure. This is the toughie sometimes. At 298 in 1 atmosphere, bromine is a liquid with a high vapor pressure. Okay, so you imagine it's liquid, it's vaporizing, and chlorine is a gas. They're next to each other in the same column on the periodic table. Those observations provide evidence that under the given conditions, the forces among bromine molecules are stronger than among chlorine molecules. Forces among chlorine are stronger than the chlorine-chlorine bond. The bromine-bromine bond is stronger than the chlorine-chlorine bond, and the opposite is in letter D. Now remember, when you're vaporizing something, you're not breaking chemical bonds. You're only breaking the intermolecular forces between them. So you'll see these distractors talking about chemical bonds being broken. Please ignore them. You'll be tempted to pick them. That's why they're put there, but you want to just say, all right, we're not bonding, we're not breaking bonds, we're breaking intermolecular forces. So we're going to go with A on that. All right, quick pause the video moment again. Hopefully you're practicing along. Here we have a more complicated one. We have 4 different liquids in flasks at 20 degrees Celsius are represented above. The table below identifies the compounds. So we have pentane through octane, adding a carbon in each time. Flask C shows the most particles in the vapor phase. Which of the following is not shown in the model but best helps to explain why flask C must contain pentane? Take a moment, pause the video, and choose your answer for this one. Okay, and if you picked letter C, congratulations. This model is not showing the random motions, but it doesn't really need to. We're just kind of worried about why there's more in the vapor phase here. The relative speeds of the vapor particles, that could change as well, but again, it's not relevant here. The structural formulas could be included, but we already have the chemical formulas, which are close to being the structural formulas. The real big thing here is the strength of the intermolecular forces between the particles in the liquids. Because pentane has the lowest boiling point, that tips us off that it has the weakest intermolecular force and therefore the strongest vapor pressure, or the most molecules vaporizing in there. All right, we're doing really well. Let's do a couple more vapor pressure. I'll do a couple and then I'll have you try one more with that. All right, so we have again a table with some substances, Lewis diagrams, and boiling points, which are, this one's a little bit higher. Compared to the equilibrium vapor pressure of CH3OH at 300 Kelvin, the equilibrium vapor pressure of the ethanol at 300 Kelvin is. Okay, before I'm even going to look at the answers, let's take a look at this. This one has a lower boiling point. This one has a higher boiling point. A lower boiling point means that generally the vapor pressure is higher because it reaches the boiling point, the 760 torr in the atmosphere, and reaches and exceeds atmospheric pressure at a lower temperature than one that has a higher boiling point. So lower boiling point, weaker intermolecular forces, stronger vapor pressure. Higher boiling point, lower vapor pressure. You got to remember they're opposites. So the vapor pressure of this one is going to be lower. Okay, I've got 2 answers that say lower because we have London dispersion are greater than those among CH3OH. Yes, that's true. This one will have a higher London dispersion force because it's a little bit larger, but lower because the larger number of hydrogen bonds among C2H5OH. Okay, hold on. I'm going to go back for a second. They actually have the same number of hydrogen bonds, 1 on each side. So they'll do some hydrogen bonding. The difference here, I'm going to change my answer and go back to C. It's lower because the London dispersion forces are stronger because they both do hydrogen bonding. All right, I'm going to talk about this one because you may not know what a cis or trans isomer is. This throws it in there. Look at these 2 molecules. And in this case, they're the same set of elements, but in this case, the chlorines are on the same side, and we use the cis prefix for that. They're on the same side of a double bond, and they're not going to rotate. A trans goes across the double bond, so 1 on this side, 1 on this side. The structural formulas for 2 isomers of 1,2-dichloroethene are shown above. Which of the 2 liquids has a higher equilibrium vapor pressure at 20 and why? Okay, so we got to think it through. Higher vapor pressure means lower intermolecular forces. So maybe the one that's more non-polar from that. And I'm looking at this one. This one seems kind of polar because the chlorines are both on the same side. Chlorines here are on opposite sides. So I'm going to go with the trans isomer having the higher equilibrium vapor pressure, which gives me C and D. And it has, because it has dipole-dipole interactions, whereas cis isomer only has London dispersion. And this is the opposite of that. It's trans because it only has London dispersion, whereas the cis has dipole-dipole. And that is where I'm going to choose my answer on that. Okay, it's your turn. We're nearing the end of our video. Take a moment and take a look at these two compounds. Their molar masses, this one's about double. And their boiling points, again, this one is getting close to double. Based on the information in the table above, which liquid, CS2 or CCl4, has the higher equilibrium vapor pressure at 25 degrees and why? Take a moment, pause the video, back in a couple seconds. All right, again, because the second one has the higher boiling point, that means its vapor pressure is the lower. And this one has the lower boiling point, so its vapor pressure is the higher. So I'm going to choose one of the CS2 answers. And we have because it has stronger London dispersion forces, or CS2 because it has weaker London dispersion forces. So you get all combinations here. Lower pressure, lower vapor pressure means stronger intermolecular forces. So let's go with A on that. All right, the last two, I just wanted to show you a couple of things you might see once in a while representing hydrogen bonding for this one. This one's a lengthy question, and it gives information about thymine and adenine form a base pair in the DNA molecule. These two bases can form a connection between two strands of DNA. Which of the following diagrams shows the correct representation of hydrogen bonding denoted by dashed lines? Okay. You'll see diagrams where they'll have molecules interacting and they'll ask, hey, point out which one has the correct hydrogen bonding location. You're looking for hydrogens on one molecule attached directly to the lone pairs on an oxygen, a nitrogen, or a fluorine. So for example, this hydrogen is attached to a hydrogen, that's not a hydrogen bond. This hydrogen is attached to a hydrogen, that's not a hydrogen bond. Up here, we have hydrogen attached to a nitrogen, which is great. That's a hydrogen bond. But this nitrogen and this oxygen, that's where the double bond has been drawn. That's not a hydrogen bond because there's no hydrogen in it. So not that one. I'm working in reverse here. Here's a hydrogen attached to an oxygen or nitrogen. Here's a hydrogen attached to an oxygen. And you gotta imagine there's lone pairs on those. That looks pretty good. Just to double check this last one, we have. So both A and B have hydrogen bonding to other nitrogens and other oxygens. The difference being that these hydrogens also have to be bonded to a nitrogen or an oxygen themselves. So it's got to be bonded directly to a nitrogen, oxygen, or fluorine, and then hydrogen bonded to one of those three as well. And the only one that fulfills that category is letter D. These hydrogens up here are on carbons, which doesn't count for hydrogen bonding. Okay, great. And the last one I wanted to show to you was this one. We won't do a pause the video moment here, but here's a nice looking diagram of some diatomic molecules. The diagram above is a molecular model of a gaseous diatomic element that is just above its boiling point. Intermolecular forces between the gas molecules will cause them to condense into liquid phase if the temperature is lowered. Which of the following best describes how the model is limited in its depiction of this phenomenon? And it's a nice looking molecule. You can read the descriptions here in the answers. It does not show how hydrogen bonds are constantly forming. That is not the correct answer because if it's diatomic, it's nonpolar and it does not have hydrogen bonds. So it does not show how interactions between ions. Ions, again, we're not looking at ions, we're looking at diatomic molecules. Permanent dipoles, strike 3. This one doesn't work because, again, we have nonpolar molecules. And it does not show how temporary fluctuating dipoles of the molecular electron clouds result in a net force. And that, because we're dealing with diatomic molecules, is the answer. So I hope you found this helpful. We went through about a dozen or so multiple choice questions on intermolecular forces. If you have questions, send them to me in the comments or directly. And in the meantime, happy studying and have a great day.